allow me to just briefly introduce about our research group here in UTM, which is called the Power Electronics and Drive Research Groups. We have 11 members within this group with diversified research interests, as you can see here, ranging from the active filters, harmonic mitigations, to electric vehicles, to the multi-level inverters control and design. If you are interested to know more about our research group, you can visit this website here. We always open for any collaborations with everyone. All right, so here is going to be my contents, and I think I will be also struggling with time, like Mr. Nick before just now. The contents is going to be is broken into 3 parts: the background, modeling, control, and the research on the high-performance 3-phase induction motor drives. I will talk about the modeling of the 3-phase VSI, which depends on how you control the VSI, the 3-phase induction motor model, and then I will talk some basics on the FOC, the field-oriented control, the direct torque control, as well as the predictive torque control of the induction motor drives. Okay, and then later I will talk on the high performance, some of the research works that we have performed here in UTM on the high performance 3-phase induction motor drives. All right, some background and history about the high performance drive. The high performance of induction motor drive is basically characterized by the precise torque, speed, or position control of the motor drives, which is the 3 most common variables that we want to control in electrical drives. And on top of that, this response, which is especially the torque response, has to be good, and good dynamic response as well as good steady state response. To achieve this control, these characteristics, we need to have the torque and the flux components. The control of the torque and the flux component in the machines has to be decoupled, which means that it has to be independently controlled. Controlling the torque will not affect the flux and vice versa. And this happens to be relatively easy in DC motor, as we all know that, because in DC motor, you know, the torque, which is the armature current, is always quadrature to the field flux, which is produced by the field current or by the stator, or which can also comes from the permanent magnet due to the commutator and the brushes actions, which is the mechanical commutator and the brushes. But this thing is not going to be that easy for the induction motor. Okay, the coupling, the decoupled control of the torque and flux is not going to be easy for the induction motor, because the torque, the stator flux and the rotor flux, which is interacting to produce the torque, is not coming from the different source. It is coming from the same source, which is the stator voltage. So the decoupling of this component is not going to be as straightforward as we can see or we can have in the DC motor. Let's look back a little bit on the history of this high performance motor drive. You know, before the power electronics was introduced, the high performance speed control for any applications which require high performance speed control or precise speed or torque control is conducted or is performed using the multi-machine configurations, which is known as the Watt-Leonard configurations. In which you have, in order to control the speed of the DC motor, you have to have a variable speed, and then that variable speed is coming from the generator, which is run or which is coupled to the induction or AC machines, which is running at a constant speed. And we change the output of the DC generator by changing the field excitation. And then the SCR was invented in around 1958 there, which changed the whole thing, because now the inverter is later invented, in which the variable frequency and the variable voltage supply is now available, which can be used to directly control the AC motor instead of controlling achieving it using the DC motor. However, during those times, during when the inverter was invented, not until the 1970s, when the field-oriented control was introduced, the high performance application is still dominated by the DC motor, because there is no way that we can decouple the torque and the flux during those times. But then I would say that the first breakthrough in AC motor drives is when the FOC was introduced around in late 60s, early 70s by the two Germans, Hasse and Blaschke, which was then later commercialized in 1980s. FOC basically transformed the induction motor into similar to that of the DC motor, in which the torque can be controlled precisely and quickly, as similar to what we have in the DC motor. And then a second breakthrough in AC drives, I would say the inventions of the direct torque control in 1984 and the direct self-control, which are basically almost the same control strategy here, which was developed at different parts of the world. One in Germany, the other one is in Japan, but they published the papers around the same area, which is in 1984 and 1986. It was then commercialized by the ABB in 1990s. And the recent development in AC motor drives now can be seen is the applications of what we call the model predictive control, MPC, to the motor drives and power electronics systems. The MPC, or the model predictive control, was applied to a slower system with larger time constant before, like for example in the petrochemical system, but it was then applied to the power electronic systems around starting in the year 2000. So in this talk, I will be talking about these three control techniques, which is the FOC, DTC, and MPC. All right, so let's look at on the modeling and control of the voltage source inverter first. This is the circuit diagrams of the inverter with IGBTs. So you have three legs there, and then these each of the switch, or each of these power semiconductor devices is actually operated as a switch, which means that it is convenient for us to replace it just by a switch, since the operations of these semiconductor devices is just whether to turn on or turn off, or similar to the operations of the switch. Now, the most widely controlled techniques of the voltage source inverter is to use the pulse width modulator, which the most common types of modulator that is used now is, I think, would be the space vector pulse width modulations and the sinusoidal pulse width modulation, which is based on the comparisons between the sinusoidal and the control signals. The way we do it is that we are actually linearizing the output voltage of the converter over time, switching time, which means that we are actually removing the nonlinear behavior of the inverter by linearizing this behavior, which means that the relationships between the reference signals and the outputs becomes linear, which means that once we do that, then we can control the inverter using a linear regulator, such as the PI controller here, which is shown here, which is used to control the current. Okay, in order to control current, then you have to have a feedback. This is the motor, this is the VSI. We have to have feedback, which is compared to the reference here, which is coming from the, for example, from the FOC, or field-oriented control controller. Now, the control in the current here is shown here is done in the two axes, because we want to avoid the interference between the phases if we control it in the three-phase environment or interface coordinate systems. And also we perform the control in the synchronous reference frame, which is typical in most modern electrical drive systems, to avoid, the problems of the lagging problem, which is encountered, which is basically caused by the PI controller, which cannot react to the moving reference or sinusoidal. If we do the control in the synchronous environment, synchronous reference frame, then everything here over this side is going to be DC. And then in order to transform back to the AC or to stationary, then we have to know the positions of the current vector, which is by estimating the frequency or the synchronous frequency there. Another way of controlling the current is, of course, which is also typically applied for the FOC, is to use the nonlinear controller, which is shown here, which is the hysteresis controller. The implementation is easy, but there is drawbacks to this hysteresis, as we all know, which is causing the high ripples as well as variable switching frequency. All right, and another way of controlling the BSI of the inverter is to directly control the inverter without using the modulator, which means that the selections of the switching states of this inverter is directly obtained from under certain conditions, which is typically used in the DTC and PTC, or the predictive torque control and the direct torque control. We shall see that later on. Okay, for this three-phase, two-level VSI, there are 8 possible switching states as shown here by this vector, voltage vectors diagram here, which can also be expressed in terms of the switching states of the inverter, SA, SB, and SC here, where S can be either 1 or 2, 1 or 0. If it is 1, then the upper switch of the leg is turned on, and if it is 0, which means that the lower leg of the switch is turned on. All right, so now let's look at on how the induction motor is controlled. Is modeled first. This is a diagram of the three-phase induction motor. You have a three-phase axis there for stator, for the ABC, and also the three-phase axis for the rotor. This axis there is actually showing the magnetic axis of the stator and as well as the rotor. The angle there is the angle between the axis of the stator, the magnetic axis of the stator, and the magnetic axis of the rotor. Now, modeling this three-phase induction motor in the ABC coordinate system is very complex because of the magnetic coupling between the stator phases, the rotor phases, as well as the stator and the rotor phases. You will end up with a very complex equation. For example, here, this is the stator voltage equations expressed in the where VABC and the rest here is basically a vector, as well as this is the rotor voltage equations, which describe the rotor circuits. Okay, D psi D ABCC and D psi ABCR there is the induced voltage due to the rotating flux, which is coming from the stator as well as from the rotor currents. And if you write down this equation in terms of the matrix, which is shown here, you can see that these two dash box here represents the relationship between the voltage and the current, the voltage of the stator and the current of the rotor current, as well as the voltage of the rotor and the stator of the current of the stator. And this mutual inductance which relates this is basically depends on time. For example, which depends on the rotor positions, therefore depends on time. As you can see here, which relates the the flux linkaging the stator windings, which is caused by the rotor current here, which is basically that part of the matrix here, depends on the rotor position theta r. Okay, as well as the one here, which is linking the flux, which is linking the rotor circuit, which is coming from the stator current here, also depends on the rotor positions. So the equations is basically time varying equations, which depends on the rotor positions as well as time. So in order to remove that time varying system, we will use, instead of using the three-phase modeling of the induction motor, typically in high performance applications, we use the space vector modeling techniques. Okay, this is definitions of the space vector. A is just a unique vector which represents the three-phase separations, space distribution windings on the three-phase induction machines. For example, if you have a three-phase sinusoidal voltage there, and at a particular point of time shown here, then the space vector can be represented by just adding the three terms there, which is phase A, phase B, and phase C. At that point of time, you see that phase B there and phase C there is has a negative value, which is the reason why you have that negative part of the vector there. Okay, this is the positive B, positive C. You have a negative C and negative C there. You just multiply the instantaneous value of VB with A and instantaneous values of VC with A squared, which is given by that vector there. Then you will add that, and then you get the resultant, which is shown by the black vector here. If this is sinusoidal, meaning that black vector there, that black the resultant, which is the space vector of the voltage there, is basically going to be rotating at a speed which is determined by the frequency of this three-phase voltage supply here. Now, this voltage vectors is a complex number, which means that we can actually resolve that into the dq axis by taking the imaginary part, the real part of that vector. Then we obtain the real part of that vector which can be written in terms of the VA, VB, and VC there. And if we take the imaginary part of that vector, then we obtain the Q part, or the imaginary part of that vector, which can be represented by a vector shown here. Now, if this vector is multiplied by what we call the vector rotator there, which is e to the power of minus j theta, what happens is that you can actually you are basically introducing another coordinate system here, which rotates at a speed which is determined by that rate of change of that angle alpha there. Okay, for example, here, if you multiply that, then you will get these equations here, which means that if you draw the vector here, then you can see that there is a new coordinate system which is basically rotating, which is defined by that angle alpha there, which means that if this coordinate system rotates synchronously with that vector, as I said earlier, at a synchronous speed, then if we resolve the d and q component of this vector to this rotating axis here, then we will see that this d and q component is basically DC quantities, which is very convenient later on for us to develop the FOC control algorithms. All right, so if we apply these transformations from ABC to the space vector for these induction machines, we will end up with these equations here, which is expressed in the space vector, the stator and the rotor voltage equations. But however, since the rotor is still moving relative to the stator windings, the dq axis of the rotor is still moving relative to the stationary dq axis of the winding, there will still be a mutual inductance between the stator and the rotor, which will depend on the rotor positions, okay, which is not good for us because that will, you know, resulted in a time varying nonlinear system. So in order to remove that time varying component there, which is the coupling between the stator and the rotor, what we can do is we can transform everything into the same reference frame, which is either stationary or moving, which means that there will be no relative motion between the dq of the stator and dq of the rotor, which means that now the coupling or the mutual inductance between the stator and the rotor now is independent of time, which is not changing with time. And we can, based on that, we can actually write down the equations of the space vector here. As you can see here, the flux linkage of the stator now is no longer containing the time dependent component, which is depending on the rotor positions there anymore. So, and we can also express this voltage in any reference frame that we want, any arbitrary frame which is rotating at any arbitrary speed. All right, and then combine these equations with the torque equations, and we have a complete model of the induction motor, electrical model of the induction motor, which will be used later on to develop this FOC, DTC, and as well as MPC or the PTC. All right, let's look at the first modeling, which is the field-oriented control. There are various types of FOC. You can have the stator flux FOC, for example. You can have the rotor flux FOC. You have the magnetizing flux FOC, which depends on how you define the orientations is. Okay, if you are orientating everything to the rotor flux, then we call the rotor flux FOC. What I'm going to discuss here is just the rotor flux FOC, in which everything is oriented to the coordinate system, which is fixed or aligned to the rotor flux. And in order to do that, we have to define the torque in terms of the rotor flux and the stator current, which is shown here, which is expressed in the dq axis here. All right, so if we draw this vector of this rotor flux and the stator current and resolve this component into its d and q component as shown here, as you can see that in order to control the torque here, it's not going to be easy. All right, for example, if I control the torque by controlling the stator current, which is only accessible to me or to us, the stator current is accessible to us, not the rotor flux. Okay, then I will also affect the rotor flux Q component here, which is on the other side of these terms of expressions of the torque here. All right, and if I just controlling the D component of the stator current here, I will also affect the D component of the rotor flux, which is completely different from the torque expressions that we've seen in the DC motor, where we have no coupling between the torque and the flux component. If I just control the armature, then that will not affect the flux. All right, so in order to transform this into the torque expression similar to what we have in DC motor, what we can do is that we define a new coordinate systems here, which is which is aligned to the stator flux, sorry, to the rotor flux here, which means that the Q component of this rotor flux in our new coordinate system, which is rotating synchronously with the rotor flux, is going to be equals to 0. All right, there is no Q component in this rotating reference frame here, and which means that we can control the torque easily, because everything now, the torque equations now can be transformed into a new form of equations, which is shown here, where we remove the Q component of the rotor flux, and the D component of the rotor flux is, in this case, is equal to the magnitude of the rotor flux itself here. All right. So this, as you can see, if you compare to the torque expressions of the DC motor, is similar, has the same characteristics there, in which you can quickly control the torque by controlling the Q component of the stator current in this rotating frame. All right, and you can fix the flux by keeping that D component of the stator current. And remember that this rotating coordinates here is rotating synchronously with the rotor flux here, which is rotating synchronously with the stator current vector here, which means that everything here, when you resolve this to this DQ axis here, is going to be appear as DC, right? So in order to implement this, then we have to know the positions of the rotor flux, which is, for us to transform from the stationary to this rotating, and then from the rotating to the stationary back, in order to implement the current control. And in order to do that, there are two types of control or method to do that, which is the indirect or the direct FOC. I'm just going to discuss the indirect FOC due to the time limitations here. As you can see here, you have the rotating frames here, which is everything expressed in the DC quantities, which is controlled in the rotating frames. And we have the stationary frames when it comes to the implementations to the actual hardware circuit here. And in order to transform that rotating frames to the stationary, we have to know the rotor positions there, right? So the how to obtain that reference signal, the stator current D and Q component, as well as the sleep of the rotor flux, is to examine the rotor flux voltage equations here. Right, this is the rotor flux voltage equations expressed in the rotating reference frame, and since we cannot access the rotor current here, the rotor current is substituted with the rotor current obtained from the rotor flux linkage equations here. And then if you substitute that into this equation here, then you end up with these equations here. And then if you resolve this into the D and Q component here, then you can see that you will end up with these two equations here. As you can see here, that the flux in this rotating frame here is basically just the magnitude of the rotor flux. And then there is no Q component of the rotor flux equations here. All right, and then the difference in the speed there, which is the speed of the rotor flux and the rotor speed there, is basically the sleep. So combining these two equations here with the torque equations, then we can actually derive the reference for the stator current D, the stator current Q, as well as the sleep, right? Which is what we need. All this expressed in the rotating reference frame. Then once we have that, then we can implement the control of the FOC, which is shown here. All right, so we have the three equations there to derive the D and Q of the stator current in these rotating frames, which is derived from the reference torque and the reference flux here. And then in order to implement that, we have to transform that back to the stationary frames there, and we obtain the rotor flux positions by adding the sleep, which is also calculated from there, with the rotor voltage, with the sense or with the speeds of the rotor, which is using a sense using the mechanical sensor there, and then integrate it to get the rotor positions. As you can see that the structure here is a feed-forward structure. The direct FOC, on the other hand, which I'm not going to show, is the has a feedback structure, and this forward structure here is very sensitive to parameter variations. Which is one of the main problem of the FOC. Now let's move on to the direct torque control now. The direct torque control is basically is introduced or by you know, the Japanese one, the Japanese professor and the German professor about a decade and a half after FOC was introduced, right? The structure, as you can see here, is very simple. It has no frame transformation. It has no a current control regulator here. The selections of the voltage vectors is determined by this voltage vector selector, which is basically a lookup table, depending on the torque and the flux demand, as well as the rotor flux positions there. All right, so the question is, of course, how you build that voltage vector selector there in order to control the torque and the flux at the same time. All right, so let's see how the flux is controlled first. We start off with the rotor flux stator voltage equations here, and then approximating the ohmic drop across the RS there is negligibly small. Then we can say that the change in the stator flux is equals to the voltage vectors times the change in time, all right, based on that equations there, which means that we can control the change in the stator flux by selecting the suitable voltage vectors. There are 8 possible voltage vectors which is available for us to select from the 2-level 3-phase voltage source inverter, right? For example, if this is a stator flux vector there, and I want to control the change or the directions of the profile of this stator flux vector, then I can choose a voltage vector, for example, given by V4 there. You know, this is the states of the switching vector of this 3-phase voltage source inverter. By doing that, then I will direct a new positions of the stator flux there. Then if I want to move further the stator flux to a new directions, then probably I can choose V5 there. That will give you a new state or positions of the stator flux there. Combining the two in a very short time, then you will have something like that, in which I can control the projectile or the profile of the stator flux to whatever profile that I want by selecting a suitable voltage vectors. Now for the DTC drive, we typically hold the stator flux constant within the base speed, and then that will result in a circular profile of the stator flux. We control the stator flux by controlling it within the hysteresis band of the stator flux, which is defined by that, and we also divide the stator flux plate into 6 sectors there. For example, if I am in sector 1 there, okay, then in order to control the flux within the hysteresis band, then I will choose V3 and V2 there. Then if I move to the new sector, then I will choose a different set of voltage vectors, which is V3 and V4, and so on to sector 3. Then I will move to a new set of voltage vectors until sector 6 there, which I use a V1 and V2 again to control the increase and the decrement of the stator flux. All right, or in general, if you are in the kth sector, then you can have K+1 vector to increase and K+2 vector to reduce. For example, if I am in sector 3, then I will use 4 sector voltage vector 4 to increase and voltage vector 5 to reduce the flux. The question is now, how are we going to use the same vector to control the torque? All right, because we have to control the torque and the flux at the same time using the same voltage vectors. We do that by looking at the voltage, looking at the torque equations as shown here, in which the flux or the torque is basically controlled by controlling the angle between the stator flux and the rotor flux. This is the magnitude of the stator and the rotor flux, which is held constant within the hysteresis band. All right, so if you can control the angle, then you can control the torque. For example, you have the stator flux here and the rotor flux there. This is the angle between the two. If I select a voltage vectors to increase the flux here, and at the same time, I will increase the angle, meaning that by doing that, I will increase the torque as well as increase the flux. On the other hand, if I choose a voltage vectors, which is to reduce the flux, but still increasing the angle, then I will increase the torque, but now I'm decreasing the flux. Right. Another way is to use the active reverse voltage vector, which is opposing the rotations of the flux, which means that if I use increase the flux there, then I will reduce the angle, which means that by controlling the flux, by controlling the torque, which is reducing the angle to reduce the torque, I will also increase the flux. Now, if I choose a different voltage vectors, that will also decrease the angle, which is also increase the torque, but now reducing the flux, then I will also increasing the torque and reduce the flux. There is another, the third last way of doing to control the torque is to just apply a zero voltage vectors, because we know from the equations that zero voltage vectors will end up with the state of flux not moving or not changing with time, which means that what happened is that the rotor flux will move closer to the state of flux, which means that the torque will decrease slowly. And this when this happens, the flux is basically it's not moving. Theoretically, will not move with time because of the zero voltage vectors application. So by selecting the suitable voltage vectors, depending on the sector or the positions of the state of flux, there we can use this lookup table here, which is shown here, to select the suitable voltage vectors to simultaneously control the torque and the flux demand, which, as I said, depends on the flux positions here. Okay, let's move on to the last control, which is the predictive torque control. I'm sorry, I'm going very fast here to catch up with the time here. All right, the MPC is basically, as I mentioned here, is applied to a system with slower process time or larger time constant before, like for example, in the petrochemicals in early 1990s. But the applications to the power electronics only appear around in the year 2000s, where the fast processor, with the help of FPGA, for example, is made it possible for us to apply this MPC in real time for the power electronic system, which much smaller time constant. Okay, according to these classifications of, before that, let me just give a credit to the three pioneers of the MPC, which I think is going to be Professor Holtz, which wrote a paper or applied this MPC earlier in 1984 during that time to control the current. And then we have Professor Cannell, which is famous for his generalized MPC. And then we have Professor Rodriguez from Chile, which is famous for his finite control set, FSC MPC. According to a paper which is shown here, the classifications of MPC can be classified into two types, which is the continuous control set, where the actuating signals, which is basically can be a voltage reference, for example, is a continuous signal, which means that in order to implement the CCS MPC, we have to have a modulator. And then later, Rodriguez introduced what he called the finite control set MPC or FCS, in which the modulator is not at all. And the implementations of MPC is very much simplified compared to the continuous control set CCS MPC, which is shown here. All right, FCS MPC can be further classified into two types, which is the OSS MPC, which is the optimal sequence switching MPC, which has the prediction horizon, which is more than two or more higher, which means that the prediction is performed as 2 steps ahead or larger. And then we have a short prediction horizon, or called as the optimal switching vector MPC, in which the prediction is only performed a step ahead, where n is equals to 1. This is also known as a predictive torque control here, which I'm going to talk about here very briefly here. So the model is basically developed using the original without any modulator there, the converter. And then the feature of PTC is very intuitive. We can incorporate nonlinear functions of the model into the PTC algorithm. Does not require a modulator. And it is also possible to remove the cascade structure of the drive systems, all right, if we want to remove it. And then another powerful feature of the PTC is that the constraints can be added to the cost functions. Let us look at how this works. For a 2-level voltage source inverter, we have 7 possible models that we can predict. Okay, because two-level 3-phase voltage source inverter has 8 possible voltage vectors, 2 of which are zeros. So there are 8 possible models that can we predict, or we can use to predict the behavior, the torque and the flux there. And then by using this prediction model, we will select the cost function, the voltage vectors that will give the least value of the cost function. you can see the main difference between PTC and the feedback structure is that, you compare the reference here with the future value. Whereas in your feedback system, you are comparing the reference with the already happened control variables, which is, you have a feedback system. Here we are comparing that with a future value, which means that we have the options of selecting which of these voltage vectors will minimize the cost functions here, right? Let's look at one by one here particularly for this PTC here. The state observer, which is to estimate the state of flux in the rotor flux there. We can use the three equations from the voltage vectors equations, the space vector equations of the induction motor that we have seen before to predict the state of flux and the rotor flux by discretizing the stator voltage equation using the Euler forward method, right? So we have the predicted value of the state of flux here, and then from there we can use the rotor flux linkage equations in order to predict the rotor flux. This predicted state of flux and rotor flux is going to be used later to predict the torque and the state of flux, which is shown in the next steps here. In order to predict the torque, then you have to use the future value or the predicted value of the stator current, as well as the predicted value of the rotor flux. Now, the predicted value of the stator flux is obtained from the same equations, but instead of using the current the previous values of the stator flux, we use the estimated values of the stator flux, which means that we can use that, we can obtain the predictions of the stator flux there. To predict the current is going to be not that straightforward. You have to use all these four equations here to derive these equations shown here, all right, which is the predicted current, where the constants there, the tau sigma, the r sigma, and kr there, all depends on the parameters of the machines. Now, the cost function is very, very powerful because you can actually add the simplest one, for example, for this PTC here, is where you want to minimize the torque reference with the predicted torque reference, predicted torque here, and you also want to minimize the torque flux reference with the predicted flux value here. WT there is a weighting factor, which is because these two units are of different, these two variables are of a different unit, then you have to have that weighting factor there to emphasize which one is more important than the other. All right, so this is the most basic cost functions for this PTC to minimize that error. All right, you can add, as I said, constraint to this. For example, if you add a constraint to the switching number here, where n is the number of the difference between the predicted switching states and the previous states, then if you add that, then that will also minimize, which means that we will try to minimize the switching frequency of the inverter there, okay, by adding that simple term there in the cost function. For example, if you can see here, this is the torque reference without n or with lambda there, which is the weighting factor set to 0, then we have a torque response here, which is very fast, as you can see, and this is the voltage vectors which is used to select that voltage vectors. Now, if I add the component of the switching frequency there to the cost function, then I will get a different waveform here, where you can see now that the switching is reduced. All right, the switching of reduced. The good or the most important behavioral characteristics of these two waveforms is you can see that you can reduce the switching frequency, but you are not compromising that with the torque response. You see, the torque response there is still good as with a higher switching frequency, which is not possible at all if you are using a linear regulator, where you have to compromise between the dynamics of the torque and the switching frequency. All right, so I have another 5 minutes, or probably I will extend that for another 5 minutes. We have 10 minutes just to discuss on the previous research work that we have done previously at UTM, which is related to the high performance induction motor drive. For example, we have done some works on FOC, the field-oriented control, to study the modeling and the control of the structurally unbalanced induction machines, where where, for example, there's a faulty phase in one of the phases, which is credited credited to my former PhD students, Dr. Janati and Monadi. And we also have done some work on the hybrid energy storage systems, which is performed by Dr. Ari Watanasan, sorry, Ari Chaipat, sorry, Ari, what is it? The name is very complex, I can't remember there. He's from Thailand. And then we have the also done several works on DTC, which is credited to my former PhD students like Dr. Azani, Dr. Toh Chuan Ling, Dr. Ibrahim, Dr. Tole, Dr. Yahya, just to name a few. And this is what I'm going to present here in this slide here. And currently we are also doing some work on the MPC or PTC, as well as some work on DTC and the hybrid electric vehicles. Most of the motor drives research is conducted at UTM Photon Future Drive Lab, which is shown here, which is located in Skudai. So the first one we're going to very briefly look at is the variable switching frequency and high torque ripple problem, which is typically the problem faced by the hysteresis-based DTC. You know, theoretically, the switching of the inverter occur whenever the torque touches the upper and the lower band of the hysteresis torque control here, as you can see here. All right, whenever it touches the upper band, there will be a new state of switching states here that has to be selected. Whenever it touches the lower band here, then you have a new switching states that have to be selected, which means that the switching frequency basically depends on the slope of the torque, and the slope of the torque in this case depends on the operating conditions, which are the load torque, which depends on the speed of the motor, which depends on the DC voltage, and so on. So you end up with a variable switching frequency, which is not good for motor drives, because that is very difficult to, for example, design the filter for the inverter. Then you have to use you don't know what is going to be the switching frequency because it is variable. Then it is difficult to design the filter, as well as you will not be utilizing the capability of the switching devices at its highest capability, because you have to determine the worst case conditions in order to select the switching devices, right? Now, there's another problem with the DTC implemented using the hysteresis comparator, is that ideal implementations that you will have the torque confined within the hysteresis band. But when you implement that digitally, then you can see that the torque can go beyond that. For example, if you do a sampling somewhere here, then the next, sampling here, then the next sampling happens here, in which the torque already pass through beyond the torque reference here. All right, and this thing get worse is if the sampling is larger. All right, so two problems: variable switching frequency and higher torque ripple. This is the actual waveform obtained from the actual drive systems. As you can see that the circle there mark the conditions in which the torque goes beyond the hysteresis band or the reference here. And in fact, it touches the upper band there, which causes a reverse voltage vector selections, and then further causes the torque ripple, as you can see there. Now, in order to overcome this problem, because the root cause is basically coming from the hysteresis controller there, what we do is that we just replace that with what we call the constant switching frequency controller, and we managed to publish this in the IEEE transactions on industrial electronics. Where the hysteresis controller that is replaced by a familiar linear regulator, which is similar concept to the current control regulator, where we can use a PI controller to design the controller there, to design the control system there, which means that we have to linearize the torque loop, average and linearize the torque loop, and design the PI controller using the the convention, using the linear control system design tools. All right, this is the implementation of the systems. As you can see, this consists of the DS1104 or DS1103, and then we have the FPGA to implement the lookup table. We have the voltage source inverter there. This is the picture of the hardware there, and this is the results. You can see the hysteresis controller compared with the constant switching frequency that which reduce the ripple there, as well as you can see that, however, you can see that the torque dynamic is slightly degraded there with constant switching frequency, which is what we expect, because hysteresis controller, as I said, has a very excellent dynamic response compared to the linear regulator. This is the spectrum of the current. For the hysteresis, you have a distributed frequency spectrum, whereas for the constant switching frequency, we have a fixed switching there, which occur at 2.2 kilohertz there. Next step is that we remove the flux as well, hysteresis controller, with the constant switching frequency controller, and we managed to publish there in the also in the IEEE transactions on industry applications, where we need to model the torque loop there, okay, by again linearizing and averaging and linearizing the torque loop, and then we can therefore design the linear controller, the PI controller there, in order to control the flux. And this is the results that you can see that this is switching at a much higher switching frequency of around 10 kilohertz, because we use the FPGA to implement the controller instead of the DSP or the processor. We use the FPGA to implement the controller, so which allow us to increase the switching frequency up to 10 kilohertz. And you can see that the ripple is almost not there from this scope, and the current is has a smoother with a much lower harmonics there compared to the hysteresis implementations there. This is the spectrum of the current. As you can see that it is more defined at 10 kilohertz there, around 10 kilohertz at the switching frequency of the torque controller, when compared to the more distributed, switching frequency when we implement it using the hysteresis controller. The next work on the DTC is to look at on the dynamic over modulations and to improve the torque dynamics of the system. All right, because in the conventional DTC there is no smooth transitions from PWM to the 6-step voltage when you run the speed beyond the base speed. Okay, what we do is that we introduce a method to smoothly transit the pulse width modulation waveform into a 6-step waveform by modifying the stated flux voltage vectors before it is fed to the lookup table. All right. We managed to publish 2 papers here in the IEEE transactions on power electronics, as well as the IEEE transactions on the industrial electronics. One on the dynamic torque, one on the dynamic over modulations. The other is to improve the dynamic torque. This is the implementation. As I said earlier, you add that modification block, the output of that hysteresis controller there, in order to transit the pulse width modulations to a 6-step waveform there. We use the constant switching frequency controller, which is shown here. This is the result. This is without the smooth transitions from PWM to the 6-step. As you can see that using the hysteresis controller, you still have a pulse width modulation there, okay, which is not a completely 6-step waveform, but using the method that we introduced, you can see a smooth transitions from the pulse width modulation. This is a voltage, okay, from the pulse width modulations to a completely 6-step waveform there, which means that we basically extend the constant torque region of the drive systems in doing so. And this is the dynamic, improved torque dynamic response, where during the torque dynamic here, this is a torque, you can see that there is a multiple voltage vectors selector here due to the selections, due to the state of flux regulator there. What we propose is that to use a single voltage vectors there during the torque dynamic, which significantly improve the torque dynamics, as you can see here. All right. However, by doing so, we are compromising the torque, the state of flux profile to not becoming a circular, but there is a slight glitch there in the state of flux there because of the single voltage selections during the torque dynamics there. And then the final one that I would like to share is the one which is constant switching frequency here. Drive systems, also DTC, but we have also found out by using the constant switching frequency controller, we managed to improve the flux regulations. And by improving the flux regulations, we also managed to improve the speed estimation. And the speed estimation that we perform here is using a standard EKF-based estimator. And the result is shown here, where you can see that this is a step change of speed from 10 radian per second to 0. With the hysteresis there, the flux regulation is completely out of control, right? And which resulted in a speed estimation which is not going to be accurate there, all right? But with the constant switching frequency there, even though the speed goes to 0, the state of flux managed to be regulated to its rated value, which means that the estimation of the speed there, which is shown in the red there, compared to the measured value in the black there, is also improved. All right, this is the speed error there. This is the another waveform which shows during the startup, we step the speed from 0 to a very low speed of 10 radian per second there, because of the poor flux regulations at low speed there. Then you have a huge error of the estimated speed error there using the extended Kalman filter. But with the constant switching frequency controller, which managed to maintain the flux regulation to its rated value, then the speed estimations there is maintained to its, which is nicely following the measured value there. Okay, this is the speed, this is the torque there, and then this is the flux there, and then this is the current there. All right, so as a final remark before I stop is that I would like to say that the advancement of these induction motor drives is basically due to the advancements in the power electronics technology, which is the converter topologies, as well as the control topologies, as well as, more importantly, I think, is on the advancement of the powerful processor combined with the FPGA, which some of the control which was introduced earlier cannot be implemented because of these limitations, can now be implemented. For example, the MPC, which is previously only limited to the slow process system, now can be implemented to a very large, to a very fast processing system with smaller time constants, such as the power electronic systems. And it is anticipated for the drive, motor drives applications or research area. I think over the next few years, the importance, the research is going to be focused mainly around that MPC, which is a model predictive control system. All right, with that, I think I will end my presentation. Sorry for taking up more time here. Okay, thank you.